So let's start to make predictions with a transition matrix and use recursion to generate state matrices step by step. So you'll remember with recursion that that's going from step to step to step to step. We do a similar thing in this using transition matrices to define how we change from step to step, or what we say here, from stage to stage. So we have the transition matrix to describe how situations change next time. We can use this to predict what is going to happen into the future. To do this, we need to know what happens initially, at the beginning. So this is what we call the initial state matrix, the S0. So you'll be familiar with that sort of idea. We use it with the transition matrix to show the next state. So if S0 shows the condition at the start of the month, S1 shows it after 1 month. So S1 equals transition times by S0. If you continued, of course you get S2 equals to T times S1, S3 equals to T times S2, and so on and so forth. So following this pattern, and this would look familiar to you all from recursion, that we have our initial state matrix S0. The next state is defined by the transition matrix T times by the previous state, or the current state. So using that idea, we can then generate the state matrices step by step. So you'll again remember this from recursion, where we have the state that we're looking for, Sn. So n is how many steps or states along we have. T to the n, so those n's are going to be the same, times by the initial state. So you can see how we've got there, and we can write this general rule where n is the number of transitions or steps, how many states we go through. Okay. As the transitions continue, we find that the state matrix Sn settles down and the numbers do not change from state to state, year to year. Okay? They don't change. This is what we call the steady state solution, or long term. Okay? They're fairly interchangeable. Steady state, long term, I've also heard it described as the equilibrium, where everything's sort of equal. So this means that from us from the outside looking in, that those numbers that we're finding in Sn aren't changing as n changes. It looks like they're staying exactly the same. But what's happening? This does not mean that the trucks, birds, or whatever we are looking at that is transitioning are not moving. It just means that the movement is such that the numbers are the same in each state as the previous state. So you can imagine that there'll still be birds going, but then there'll be birds coming back, and at the end of all of that movement, you end up at the same place you were before. For a system to have a steady state, the transition matrix must be regular and the columns must add up to 1. We've already discussed that transition matrices, the columns must add up to 1. A regular matrix is one whose powers never contain any zero elements. Okay? Is one whose powers never contain any zero elements. So if we square it, there's no zeros. In practical terms, this means that every state represented in the transition matrix is accessible, either directly or indirectly from every other state. Okay, so yeah, you can get to each state. So to talk sort of technically for a moment, the steady state happens as n approaches infinity. So as n gets bigger and bigger, all right? We can't actually calculate, t to the infinity, because obviously that's a number that's forever out of our reach. But in reality, the value of n, we can actually find it, from between 15 to 30 or sometimes 50. That can give a close approximation, and we can do some things to check whether that is steady state or not. And one of the things we do is you must find at least 2 successive state matrices with the same degree of accuracy. So in other words, if we go, so S, I'm going to say 22, so that was equal to t to the 22 times by S0. All right, and we found that. If we go, then S23, T23, S0. If we find that, S22 and S23 are exactly the same, or have the same elements to the same decimal place. So in this example, if we've got them to 2 decimal places, they are accurate to 2, they are the same to 2 decimal places in S23, then we've found that steady state. We found it for whatever that is. So I'll say that again. So to find a steady state, we can approximate it. We can, have a bit of a guess, putting in some big numbers. Usually, n between 15 and 30 might give a close approximation, sometimes 50. But to do that, we can just guess one, and then we must find at least 2 successive state matrices with the same degree of accuracy. So if I guess n being 22, for that to be the steady state, n23 must be equal to it. Must be equal to be a steady state. And remember, with a steady state, what we're finding is these matrices, these answers, these states to be the same. We found a point where the system is just generating the same numbers. So let's look at some examples. This is from the 2018 exam 2, so extended response, a question 3. The High Roads Company has a contract to maintain and improve 2,700 kilometres of highway. Each year, sections of highway must be graded, G, resurfaced, R, or sealed, S. The remaining highway will need no maintenance, N, that year. Let Sn be the state matrix that shows the highway maintenance schedule for the nth year after 2018. So the maintenance schedule for 2018 is shown in the state matrix S0 below. So this is our initial state, and if you add it up, you'll see it's 1,400 1,600, 2,000, 2,700. That's all adds up to our 2,700 kilometres of highway. So that's always going to add up to 2,700 kilometres because it's a closed system. We're not getting new bits of road to maintain. Okay, so we can see that in 2018, our initial state, 700 kilometres were graded, 400 were resurfaced, 200 were sealed, and 1,400 had no maintenance. The type of maintenance in sections of highway varies, changes, from year to year as shown in the transition matrix T below. So you can see, okay, this is our transition matrix. This is what we did this year, and that's what we're going to do next year based on that. And you can see, if you're looking in the columns, they add up to 1. Okay, so of the length of highway that was graded in 2018, how many kilometres are expected to be resurfaced in the following year? So we've got to look at, okay, the kilometres that were graded, how many of them are going to be resurfaced next year? So there's 700 kilometres in 2018 that were graded. Now we know that of the ones that were graded, 10%, 0.1, are going to be resurfaced, R. Okay, so that's 70. So 70 kilometres are going to be resurfaced. 48% of the state got 1 mark for that, and 52% of the state got 0. Some students only gave like 10% as the answer, not, really reading it. Okay, so show that. Okay, this is a show that question, so it means that you've been given the answer, you need to show the calculation. Show that the length of highway that is to be graded in 2019 is 460 kilometres by writing the appropriate numbers in the boxes below. Okay, so let's look again at our transition matrix. Okay, we're interested in all the ones that's going to be graded. We know there were 700 kilometres that were graded this year, and of them, 0.2 are going to be graded again. So 0.2. We know there were 400 kilometres that were resurfaced, and of them, 10% or 0.1 are going to be graded. $200 kilometres were sealed, and of them, none are going to be, or 0% are going to be graded. So I put 0. And there were 1,400 kilometres that had no maintenance, and of those, 20% or 0.2 are going to be graded next year. Okay, so that is the correct answer. 77% got of the state got 1 mark, 23% got 0. Some students listed the numbers in the G column rather than the row. Okay, they were looking at there and not really so much the row. So that's understanding, okay, you've got to move from this year to next year. Okay. The state matrix describing the highway maintenance schedule for the nth year after 2018 is given by that there. So our next one is equal to our transition matrix times by our current. Complete the state matrix S1 below for the highway maintenance schedule for 2019, 1 year after 2018. Okay, so we get given that 460, which we were given here and showed how to calculate, is here. And they've given us that for no maintenance. Okay, well, let's look at our R. Okay, how many kilometres of roads are going to be resurfaced? So let's go back. All right, so I'll start with here. Of the graded roads, 10% are going to be resurfaced. So that's 700 by 0.10 plus. And of the resealed roads, 10% are going to be resealed again. And there were 400 of those, 400 resealed roads. So 400 resealed roads, of which 10% are going to be resealed again. Of the sealed roads, 200 kilometres, none of them are going to be resealed. Okay, and of the no maintenance road, the 1400, 20% are going to be resealed. So 1400 plus 20%. So 390. So 390. Now I'll do the calculation for the sealed, although you could probably see a slight shortcut there. Okay, but let's look at the sealed. Right, we'll start with the graded, 700. Of the 700 kilometres, 20% are going to be sealed. Plus of the resurfaced, 10% are going to be resealed. So 400. Okay, of the sealed, 200, 20% are going to be sealed. And of the no maintenance, 1400, 10% are going to be sealed. $360. Now, in case you were wondering, that shorthand way would have been to think Well, all of this has to add up to 2,700. So once I've calculated that, I maybe could have found that using that knowledge. Okay, so in 2020, 1,536 kilometres of highway is expected to require no maintenance. Of these kilometres, what percentage is expected to have no maintenance in 2019? Okay, so of the kilometres in 2020 that have no maintenance, what percentage of them didn't have any maintenance in 2019? Round your answer to one decimal place. Okay. Oh, by the way, this past question, that one, 82% of the state got the mark there. Okay, so focusing back here. Right, so we know in 2019, 1,490 kilometres had no maintenance. Yep, that's what that is. So, of that 1,490, we know that looking back at our transition matrix, if they had no maintenance, there's a 50% likelihood that 50% of them are not going to have maintenance the next year. So in 2019, 50% of the roads that had no maintenance in 2019 will have no maintenance in 2020. Okay. So 745 kilometres of the roads. So 745 of the kilometres of the 1,536 kilometres didn't have maintenance in 2019 either. So, divided by 1,536 and approximate equal, because I want a decimal. So 0.485, and I want it as a percentage. So that is 48.5%. So 17% of the state got 1 mark here. 83% of the state got 0. This question was not answered well, with most students giving 97%, which did not take account of the 0.5% change, 0.5 change. So what they were doing is they were just going 1,490 out of that. They just did 1,490 out of the 1536, which is wrong because only 50% of these roads are not going to have maintenance in the next year. Okay. So, in the long term, so this is our steady state, long term, what percentage of highway each year is expected to have no maintenance? N. Round your answer to 1 decimal place. Okay, round your answer to 1 decimal place. So let's go here. And first time this question, putting our transition matrix, it's a 4x4. Okay, so 0.2, 0.1, 0.2. Now remember, you've got to be pretty quick at putting these into your CAS calculator. So find ways to be quick, but you've also got to be accurate. Point 1, 0.5, 0.7, 0.8, oops, 8, and 0.5. Now I'm going to store that as a variable t because we're going to use that a lot. I'm also going to make putting my initial state. So that means that there's one column. Oops. And 4 rows. Okay. So this was 700, 400, 200, and 1400. And again, I will assign that to a variable because we're using it again and again and again. Okay, so we're looking for steady state. So you can see, so T times S, you can see that transition's happened there. That's that 2019. We should recognize that. If we went T squared, that's by S, that's the 2020. You can see the 1,536 of not maintained road that we were told about in the question before. So we are looking for that steady state. So I'm going to just pick at random some largish numbers of n of this to put t to. So I'm just going to guess, I don't know, 17. S. Okay. So let's go t, and to check it, t to the 18 times by S is that is steady state, isn't it? Because they've not changed. They've not changed. Okay, so let's go back to our question. Let's go back to our question. In the long term, what percentage of highway each year is expected to have no maintenance? So we found that steady state, 431.6, 388.4, 347.9, just because otherwise I'm rounding. 1532.1. What percentage of highway each year is expected to have no maintenance? Okay, so we know 1,532.1 kilometres out of the 2,700 kilometres. 1,532.1 out of the 2,700 kilometres that they maintain is not going to have maintenance. So 1,532.1 divided by 2,700. So that is 56.7%. 56.7%. Okay, 39% of the state got a mark there, 61% got 0. A lot of students just gave the answer as 1,532.1 and didn't read this what percentage part of the question. Let's look at from the 2018 exam, exam 1. This is the question 8. So this is, in the hard part of the multiple choice questions. A public library organised 500 of its members into 5 categories according to the number of books each member borrows each month. These categories are J for no books borrowed per month, K for 1 book, L for 2, M for 3, N for 4 or more. The transition matrix T below shows how the number of books borrowed per month by the members is expected to change from month to month. So you can see how 10% of the people who borrow no books this month are expected to borrow no books next month, and etc., etc. In the long term, so steady state, which category is expected to have approximately 96 members each month? Okay, so you're probably thinking there's not enough information here. We haven't got that initial state. What we do have is we get told, okay, there's 500 members. So what we can do is say, well, that S0, there's 5 categories. So we're going to put 100 into each category. Okay, so in the long term, which category is expected to have approximately 96 members each month? So let's put these into our calculator. Okay, so we'll do our transition matrix first. So 0.1, 0.2, 0.2, 0, 0, 0, 0.2. So this is why I'm always saying you've got to get really quick and efficient with using your CAS calculator. And why, even in topics where you think you don't need to use it, you can just use the scientific calculator. I make you use your CAS calculator so that you can get quicker and quicker at inputting lots and lots of data. Because this is a question 8 question, we are expected to be using a little bit more time than what we would on, say, question 1, 2, or 3. Okay, so now I've assigned that to T. So now let's make my initial state. So there's 5 rows and 1 column. And with that 500 members, I'm just assigning them equally to the 5 categories. And I overwrite what's in our S currently with this new one. Okay, so we're looking for a steady state. So again, I'm not interested in what number that happens at. I'm interested in what the steady state is. So I'll just go, I don't know, 25 times by S. Okay, that's looking good, but let's check it to see what T to the 26 is. Oops. By S. All right. That's looking pretty close to a steady state. I mean, there's a little bit of difference there, isn't there? A little bit of difference. But if we're rounding them to the whole numbers, they'd all be the same. Okay, so that's looking like this second category. I'll just write that out. So 49, 96, 124, 151, and 80. Okay, so that is category K, isn't it? Category K. 46% of the state answered that one correctly, with 18% answering D and 13% answering C. Okay, now with this one, I just want to demonstrate again why this works as the steady state. Just scroll it down. So if I went like T to the 4 times by S, okay, like that. And then if I go T to the 5 times by S, you can see there's a big change there, isn't there? There's a change. They're changing. Their numbers are not steady, okay? It's not a steady state as yet, all right? It's still changing around. We haven't hit that yet. We will hit it later on. We're not asked to find where we're going to hit it though.